Machines today can do calculus, but it's our job to understand what it's doing and whether we trust it. Start with measuring a length on an axis u. If first I read a and then b, then I'll call the length b minus a, or simply delta u. Need an area? I define the area of a rectangle to be the height times the width. Need a rate of change? This is the total height divided by the total width. Now pause to notice that multiplication and division are reciprocals. This is at the heart of why calculus works. But the world has more curves than rectangles, and averages are not as useful as instant feedback. The trick is to make a strategy of approximate measures. Suppose I declare that I can measure area, or rate of change, to be exactly L. What could I offer as evidence? One strategy is you could tell me how many decimal places you plan to check. Once I know your number, I'll make a sequence of measurements in front of you and come up with an approximation to L that is accurate to within your chosen margin of error. Since you picked the error and I got below it, you have no evidence to doubt my claim. Of course, some people will be easier or harder to please, but as long as I have finally many tries to get the right precision, everyone around me will be convinced that I'm accurate. We call this the limit. With limits in hand, areas under a curve are no longer a problem. Box out a number of rectangles inside the area. Use length times width to put a number on each rectangle. Add those numbers up and call that an approximation to the area. Mathematicians have worked out when this method has a limit, and when it does, we call it the integral. It's the area under the curve, even though we never actually measured that area. Instantaneous rate of change is quite similar. Measure slopes of lines near the instants. Mathematicians have shown when this process too has a limit. We call that limit the derivative, the instantaneous rate of change. Now don't forget that multiplication is the reciprocal of division. And since integrals are multiplication and derivatives are division, together these two are also reciprocals. This is the fundamental theorem of calculus. So if we had to compute a difficult area, first we might guess a function whose derivative matches that inside. Replace that inside with the derivative of our guessed function, an antiderivative, and now the integrals and derivatives cancel by the reciprocal rule. We just need to find the total change in our antiderivative, a far easier problem. And it's okay to multiply and then divide as well. This changes the fundamental theorem of calculus in another useful way, because some areas, i.e. integrals, will always be difficult. Those we simply give names, and because we don't yet know the interval, we add a plus c to account for the fact that our constants may be wrong. This one here is called the natural log. Now if life ever serves up that function and we need its instantaneous rate of change, no problem. The derivative and the integral once again cancel, and we immediately know the answer with no real work. So if life serves you two operations that are reciprocal, and you think you can use them repeatedly to approximate reality, you might just have a calculus on your hands, which will let you sometimes rewrite your data to cancel out the hard stuff.